dynamic programming approach to solving and understanding optimal control problems. We will focus on optimal control problems with horizon length n and given an initial state x, so x0 equals x, and we will use this notation to refer to the following minimization problem. We have already studied a special case of these problems, which is when we have L being a quadratic function, L of x and u is this quadratic function. Vf is also a quadratic function, and f is a linear function. Under these assumptions, for this special case, the whole problem is convex. It is a convex optimization problem. And we can do all sorts of things to solve it. For example, we can eliminate the state sequence. Or we can use the KKT theorem to solve it. Now, before we can say more things about this problem, we need to introduce the principle of nested optimization. The principle of nested optimization allows us to address problems of this form. So, optimization problems where we have a cost function that depends on more than one variables. Here, v is a function that takes a vector of dimension n1 and a vector of dimension n2 and returns a number. And the principle of nested optimization states that if v star is the optimal value, meaning if v star is defined as the minimum with respect to z1 and z2, v of z1, z2, then we can write minimum with respect to z1 of the minimum with respect to z2 of v z1, z2. Of course, if necessary, you can take the minimum with respect to z2 of the minimum with respect to z1. The order is not important. Now, this thing here is a function of z1. And we can define this function. We can call it v2 star of z1. So what is that exactly? It is the minimum with respect to z2. So v star, in other words, can be written like this. So v star now is given by the minimization over one only of the two variables, where we have done the minimization, we have taken the minimization with respect to z2 within the definition of v2 star. So this is one thing that the principle of nested optimization allows us to do. But there is one more thing. It says that if we can find a z1 star, which is a minimizer, it is in argmin, it is in the set of minimizers with respect to z1 of v2 star. And now if we take v and we fix z1 equals z1 star, and we let z2 be free, and we minimize with respect to z2, and we find the minimizer, z2 star. So we take z1 star, we plug it in here, and now we minimize again, but only with respect to x2. And then if we can find such a pair, then z1 star, z2 star will be a minimizer of v. Now, why we mentioned that? We mentioned that because here we have the minimization with respect to several variables, u0, u1, and so on and so forth. So let's see what will happen if we apply the principle of nested optimization. And what we will try to do is that we will take u0, u1, and so on, un minus 2, un minus 1, we will split it in two parts. One will be un minus 1, and the other part will be the rest. And we'll break this minimum into two parts, and let's see what happens. So we have the given optimal control problem, and let's introduce some notation here. Let's call Vn star of x. X is the initial condition. The optimal value, so the minimum with respect to all u0, u1 up to un minus 1. Okay, we define Vn star to be the minimum cost of the problem, subject of course to the constraints. And now let's break this down using the principle of nested optimization. So you see, we broke this minimum into two parts, and now I will also break down the sum that goes from 0 to n minus 1. I will stop at n minus 2, and I will put here L of xn minus 1, un minus 1. I will just write it separately. It was previously part of this sum. Plus, of course, the terminal cost, Vf at xn. And next I will write the constraints. Now I will write the system dynamics from 0, but only up to n minus 2. And I will write xn minus 1, I will write xn separately. This depends on xn minus 1 and un minus 1. The reason we write these things separately is because un minus 1 shows up here, and I want to see it everywhere clearly in the problem. I want to identify where we have un minus 1 and where we don't. Because if you see here, the sum from 0 to n minus 2 is independent of un minus 1. This allows us now to take the minimum from there and move it inside here. Vf, and instead of writing xn, I will write this part, f, evaluated at xn minus 1. So look, what do we have here? This part, this function, is a function of xn minus 1. We minimize with respect to un minus 1, and this is a function of xn minus 1. Let's call this function v1 star of xn minus 1. And just to be clear, what is v1 star? v1 star is a function of x. We don't need to write xn minus 1. It is just a function of x, which is the minimum with respect to some variable u. So v1 is given by this equation. This is quite important. It will be important for what comes afterwards. So let's put it here in a box. And we can rewrite vn star. We have now written vn star in the following form. And I also copied the constraints. We can make a few observations here. In the beginning, the problem we started with is an optimal control problem with horizon equals n, and terminal cost Vf. Now here, the problem the equivalent Vn star has been written as an optimal control problem again, but with horizon n minus 1, you see, n minus 1, and terminal cost, a different terminal cost now, V1 star. This is the terminal cost. And if we keep doing that, we can, the next step of course would be to break this minimum down like this. Go to un minus 3, minimum with respect to un minus 2. We can break it down like that. And if we apply the same procedure, we will end up with such a formulation where v2 star is a function of x, which is given by a formula really similar to the one that came up previously. You can try that as a little exercise just to verify it by yourselves. And what has happened here is that previously, you see, we started with Vn star, which is given by this formulation where we have a horizon of n and the terminal cost Vf. And then we wrote it like that, where we have a problem which is an optimal control problem again, with horizon n-1 and cost V1 star. And then in the next step, Vn star has been written in a form that is an optimal control problem again. With horizon n-2 and terminal cost V2 star, and so on and so forth. So what we're doing here is that we start with an initial terminal cost Vf, but let's call that for convenience. Let's give it another name. Let's give it a synonym, V0 star of x. So here we have V0 star of xn. We have V0 star. From V0 star, which is, as we said, Vf, we go to V1 star, then we go to V2 star, and we can keep doing that, and at some point we will reach Vn-1 star, and at the next step, I will write it here, at the next and last step, we will have Vn star, meaning the original function, which we will have expressed like this. It will be now an interesting observation we can make here is that every time we need to carry out a minimization only with respect to one variable. And finally, we will have a recovered Vn star of x. This Vn star of x, given by this expression, is the original Vn star of x. And this whole procedure is known as the dynamic programming procedure. Now, we said a lot about V0 star, V1 star, and so on, and Vn star, and we discussed the fact that we can carry out a minimization only with respect to one variable, but at the end of the day, how can dynamic programming help us determine an optimizer of this problem? How can dynamic programming determine a U underlined star, a sequence of control actions? Of course, this will depend on the initial condition. How can it help us determine a sequence of states, the corresponding sequence of states, given the initial condition? Let's turn the page to discuss that. So once again, we said we start at V0 star, which is Vf, and we follow this procedure over here. If we know Vj star of x, Vj plus 1 star of x as a function of x can be determined by this expression. And we continue until we reach Vn star. Now at the same time here, if we take a minimizer only with respect to that u at that stage, we will need to solve the problem to find such a minimizer. We need to solve the problem argmin L of x comma u plus V0 star of f x comma u. Now if we find such a minimizer and call it kappa 1 star of x, there might be many, so I will write kappa 1 star of x belongs here, kappa 2 star of x belongs to the argmin of L of x and u plus v1 star at f of x and u and so on, and kappa j plus 1 as a function of x, these are functions of x, belong to, this is a selection from the minimizer with respect to variable u of this expression. Then we will have constructed this way a sequence kappa 1 star of x, kappa 2 star of x, kappa 2 star of x, and so on, kappa j plus 1 star of x, and the last one will be kappa n star of x. Now if we do that, I need a new page. If we do that, then the solution, an optimal solution of the problem, an optimal solution of this problem, OCP with horizon n and initial state x, is given by the following sequence: u underline star, or better, u underline star of x with initial condition x, is given by kappa n star of x and kappa n minus star of the next x, or x1 star, and so on and so forth. And the last one will be kappa 1 star of x, that will be n minus 1 star. Let's see how this works. So we start with x0 star is of course x, that is the initial condition. We use kappa n star of x0 star to compute a control action u0 star. We take u0 star and we apply to the system to determine x1 star. We apply u0 star, and from x0 star we go to x1 star. At that point we use kappa n minus 1 star to produce x2 star. At stage k in general, or stage, let's call it t in general, we use xt star and we pass it to kappa n minus t to compute the control action ut star. So this is how we produce an optimal sequence of control actions starting from the initial condition x, starting from x0 equals x. So this is what the dynamic programming method can do for us, but it can do more. If you consider now, if we call kappa star the sequence, not the sequence of control actions, but the sequence of control functions or control laws, as they are called often. So kappa n star as a function, kappa n minus 1 star again as a function, and so on and so forth, kappa 1 star. And remember, all these things are functions. What functions are these? Kappa j star is a function that takes a state from Rn and returns a control action. So if you consider the sequence of all control functions or control laws, all these, let me write it down, are control laws, then kappa star is called an optimal policy of the problem OCP n for whatever initial condition. This can be applied to whatever initial condition we have. Let's give perhaps some better notation here. We need n to remember that this has horizon n, and let's underline it to denote a sequence. So kn star underlined is an optimal policy of OCP n. There is the following result, which is why the dynamic programming approach is so much more than a method for solving optimal control problems. And this is the principle of optimality. Now, the principle of optimality states that it says let kappa n star, kappa n minus 1 star, and so on up to kappa 1 star, let this be an optimal policy for OCPN. If we have that and we drop kn star, we drop the first one, then the rest, the truncated policy, this is again an optimal policy for OCP n-1. So if you know how to solve the problem with horizon n, you also know how to solve the problem with horizon n-1 and -2 and so on. And if you truncate that sequence and you keep only k from some index j star to k1 star, so this will be an optimal policy for OCP with horizon j, which means, let me give you an example about that, which means that if you have an optimal control problem, I will write it down again. So say you have this problem, you have started by defining v0 star is vf, you have done all the procedure and you have determined v1 star, you have determined v2 star, and so on. You have determined vn star recursively using the dynamic programming procedure, and you have also determined kappa 1, you have determined kappa 2, and you have determined kappa n, and these are all functions of x. So for example, kappa 1 is, let me remind you, is an element of argmin. So suppose you have done all that, you have kappa 1, you have kappa 2, you have kappa n star, and you have done that for n equals 100. And you can tell confidently that you have here an optimal policy. Kappa n star, kappa n minus 1 star, kappa 1 star as functions, not for a given value of x, just as functions. Now, if you want to solve the problem for n equals 10, you don't need to do anything more. You have solved it already. So you have kappa 100, you have already determined kappa 100, kappa 99, and so on. You have determined kappa 10 as well, kappa 9, and kappa 1. Just drop all these values and keep these, and this will be an optimal policy for OCP 10. Now someone comes and gives you an initial x, and they ask what is the optimal sequence of control actions. That will be kappa 10 for n equals 10, that will be kappa 10 star of x, that will give you u0 star for OCP 10 of that given x. The first control action is kappa 10 star of x. The second control action is kappa 9 star of the next x. And so on and so forth. Now let's go back to the linear quadratic optimal control problem, where we have a particular L, VF, and F. So we have these ingredients, and let's solve OCP n. So we start with V0 star. We follow the dynamic programming procedure. We follow this procedure over here. So we start with V0 star of x, which is defined to be VF. Sorry, not n here. We don't need the subscript. So x transpose PFX. So that is V0. And let's go find V1 star. V1 star, as we discussed previously, is given by this equation. I will move it now here to have more space, and I will substitute L, V0 and F. And we can do the operations here. We can expand these things. Just multiplied by 1/2. Now we combine this one with this one. Second, we combine this term with this term. 1/2 goes outside. And lastly, this term by itself. How do we find the optimal value of u? This is an unconstrained problem. So how do we do that? We take the gradient of this thing inside here and we set it equal to 0. And if we take the gradient here, we will have, this is constant, so has gradient equal to 0. So this is the optimizer. In a way here, not in a way, actually, this defines kappa 1 star of x. Here is our kappa 1. Kappa 1 star of x is some matrix, let's call it K1 times x. And what is K1? K1 is this quantity. So this is K1, this is kappa 1 star. And how can we find V1 star of x? V1 star of x is the minimum with respect to u of this whole thing. But we know what minimizes that quantity. It is K1 times x. So if we copy that, once again, here we have 1/2. Let me copy that first term. So that's it, and then plus 1/2. Then we have u transpose, but u is K1x. So if you transpose that, x transpose, K1 transpose, u again, so this is K1 uppercase times x. Then u again, K1 times x. So x transpose x, x transpose times something times x, x transpose x. And if you combine now all these terms, to save time, I will just write that V1 star of x is 1/2 x transpose. You can see clearly it is quadratic. It is quadratic with some matrix P1 x. Now, if you want to know what that matrix P1 is, that P1 is given by that. This will be an interesting exercise of algebraic derivations. Just simplify this equation here, take K1 and replace it here wherever you see K1, and you will figure out that P1 is given by this matrix. And then you can see that P1 is symmetric and positive definite, and X1 is given again by a formula that is very similar to that of V0. So we went from V0 star of x, which was given by 1/2 x transpose pfx to this formula, which is again quadratic. And you know what, if you keep doing that, you will be able to find that u2 star of x, or kappa 2 star of x, kappa 2 star of x is given by a matrix K2 times x, and V2 star of x is given by 1/2 x transpose P2 times x. And we can keep doing that until we find kappa n star of x and Vn star of x. And if we keep doing that, actually, every time this one will be linear, it will be some matrix K n times x, and this one will be quadratic, let's call it Pn x. And the way to update these matrices is like that. Well, both will be no surprise, so I can copy them from here. K will be as it was here, and we solved now the linear quadratic optimal control problem with horizon n using the dynamic programming method. And on our way, we have determined kn star, kn-1 star, and so on. We can use these to determine the optimal policies of all problems with horizons up to n. So what is the optimal policy of OCP n? It is kappa n star, kappa n-1 star, up to kappa 1 star. And what is the one of OCP n-1? We'll just keep this part, and this will be according to the principle of optimality. It will be optimal for OCP n-1. Truncate, and you're done. You don't need to do it again from the beginning, and this is very convenient. Now, a few things that we need to have in mind are that, first of all, this is a convenient procedure for convex problems when the cost functions are quadratic and the dynamics is linear, and it will not necessarily work in other more general cases. It will not work to give a solution, a closed form solution, when we have non-convex problems. So that's the first thing. It's more of a conceptual tool. It is very useful, but it's not a computational tool. It is a conceptual tool. It can be used, we will be using that heavily in what follows. And the second thing we need to keep in mind is that dynamic programming produces optimal policies. It doesn't just produce a sequence of optimal control actions. It produces functions. You see here, u2 star is a u2 star of x. This k2 times x, it's the function of x. And kn star, kappa n star, is again a control law. And this defines a control policy. These are not vectors, these are functions. And dynamic programming has applications in optimal control problems, also in optimal control problems with uncertainty, and many more applications that we will explore throughout the rest of the module. So thank you very much for watching, and goodbye.